Good afternoon, ladies and gentlemen. My name is Jon Guy, and I am the President and CEO of the Waltron Group, a manufacturer of instruments for steam and water analysis systems. It's my pleasure to be here today at the vgbe Chemistry Conference to discuss a topic that is critical to the operation of modern power plants. We will review the results of Waltron's comprehensive testing and discuss what they mean for the safe operation and efficiency of your facilities. Here's a brief overview of today's topics. We'll begin with the background and concerns that led us to conduct this research. We'll then review our original 2023 test results and then introduce our new, more detailed test procedures. We'll analyze the results of these new tests, including initial upward drift, response to simulated incidents, and calibration failure tests, which highlight the critical issue of progressive electrode fouling. We'll also briefly address the impact on other measurement parameters, and finally draw conclusions on how to mitigate the effects of film-forming substances. FFAs, or more specifically, film-forming amine products, FFs, and non-amine film-forming products, FFPs, are becoming increasingly popular in industry. They offer significant benefits for corrosion protection, particularly in cycling power plants and during downtime. They form a protective, water-repellent layer on metal surfaces, thus protecting asset integrity. At the same time, we rely on high-precision online analyzers to monitor our water-steam cycles. Sodium, pH, and oxygen meters are our first line of defense against contaminants that can cause serious damage. Here lies the problem. Since operators began using FFAPs, reports of problems with the instruments have increased. We hear about loss of sensitivity in glass electrodes, membrane fouling in oxygen sensors, and contamination in colorimetric analyzers. Although the IAPWS has published several technical guidance documents, TGDs, on this topic, many operators are still unaware of the potential problems. The biggest danger here is a false sense of security. When an operator looks at an analyzer that shows stable values, they assume the plant's water chemistry is safe. But what if the device is being blinded by the same chemistry designed to protect the plant? This is precisely the question we wanted to answer. Our initial investigations in 2023 already gave us cause for concern. In this test, we ran a stable Waltron 9033X sodium analyzer continuously with a sample, adding a daily spike of 100 ppb sodium to simulate a contamination event. As you can see in the graphs, the electrode response changed drastically over time. Initially, we see a rapid and significant response to the spike. After only 10 days of exposure to FFAPs, the response time curve flattened considerably. The device became sluggish and could no longer reach the actual sodium level within the limited time frame. We also observed that the device was falsely indicating lower sodium concentrations than were actually present. This was the first clear indication that FFAs were not only slowing the response time, but actively distorting the measurement itself. These results triggered our more detailed follow-up tests. For our new series of tests, we wanted to replicate the conditions and observe the effects more closely. The main goal was to see if we could replicate the previous results, albeit at lower sodium and FFA levels. We introduced a continuous flow of 15 ppb sodium and 45 ppb FFA standard into the analyzer and collected data every 10 minutes to observe slow drift effects. To simulate an incident, such as a condenser leak, we applied a spike of 50 ppb sodium 3 times a day. We conducted 3 series of tests for both FFAPs and, very importantly, thoroughly cleaned the measuring and reference electrodes before each test to ensure a clear baseline. Here you can see our experimental setup. We used 2 high-precision dosing pumps that mix deionized water and a concentrated solution of sodium and FFA standards. This allowed us to ensure a stable concentration of 15 ppb sodium and 45 ppb FFA at the inlet of an unmodified Waltron 9033X sodium analyzer. All data was collected by a data logger. In later phases of the project, we expanded this setup to also investigate the effects on dissolved oxygen, pH, and conductivity sensors, and to test various mitigation and filtration technologies. This setup allowed us to investigate the effects of the FFAPs under controlled and reproducible conditions. The initial results of this new series of tests were immediately alarming. As the graph shows, we observed a significant upward drift in the measured sodium concentration for both tested products, from a baseline of 15 ppb to over 24 and 32 ppb respectively within 120 hours. In particular, with product A, we observed a significant accumulation of microbubbles on the electrodes. Interestingly, the upward drift persisted even after we manually removed these bubbles. This could indicate that the problem lies deeper than a purely physical blockage. We spoke with the FFAP manufacturer, who was surprised to hear about those microbubbles accumulating on the sensors. Our analysis led us to 3 likely and mutually reinforcing causes. 1. Progressive electrode fouling. The surface-active FFAs build up over time as a thin film on the electrodes. This layer acts as a barrier and distorts the electrical potential. 2. Electrochemical degradation. The microbubbles are a symptom of the electrochemical degradation of the amines directly on the electrode surface. This creates new interfering substances that further accelerate contamination. Direct cationic interference. The positively charged amine molecules are mistakenly detected as sodium ions by the sodium sensor. This leads to a positive measurement error. In summary, the analyzer is no longer measuring sodium, but is reacting to the chemistry of the FFAP itself. After understanding the baseline drift, we wanted to know how the system would respond to a sudden contamination intrusion. The results of this breakthrough test are perhaps the most concerning of the entire study. We introduced a sample containing 50 ppb sodium for just 15 minutes. The graph clearly shows 2 things. First, the analyzer's response time deteriorated dramatically. On none of the days did the reading reach a stable plateau within 15 minutes. The sensor response has become too slow to detect a rapid increase. Secondly, and even more critically, the device's ability to detect the spike at all decreases day by day. On day 1, we still see a clear response close to the actual value of 50 ppb. However, by day 5, the measured peak value for product A has dropped below 43 ppb. This means that the progressive contamination from the FFA film acts like a mask, increasingly blinding the sensor. The device not only becomes inaccurate, it loses the ability to fulfill its core function, providing timely warning of a breakthrough. The next logical question was, how does this contamination affect the calibration process, and how quickly does an analyzer fail under these conditions? For this experiment, we continuously supplied the analyzer with our sample of 15 ppb sodium and 45 ppb FFA. Once daily, we performed an automatic 2-point calibration using clean standards of 100 and 1000 ppb sodium, i.e. without FFA added. An important point here is that we did not clean the electrodes during the entire test to simulate the real-life effect of progressive contamination. We recorded the millivolt potentials and the calibration strength, i.e. the slope of the electrode. The results of this test demonstrate the gradual failure of the system in detail. For the first few days, everything seemed fine. The calibration strength, shown here in gray, remained within acceptable limits. An operator would not suspect any error here. At the same time, however, we are already seeing a clear upward trend in the millivolt readings for both calibration standards, the blue and orange bars. This is a clear indication of reference electrode drift caused by the incipient contamination. The dangerous effect of this is that the analyzer begins to report lower concentrations than actually present. It issues a false cal pass. The calibration is considered successful, even though the measurement is already inaccurate. The final failure occurred on the 3rd day. The analyzer was unable to complete the calibration because the reading for the 1000 ppb standard no longer stabilized within the specified time window due to the heavy contamination. This again demonstrates the noticeable deterioration in response time. Let's summarize the results and consider the real hazards to proper plant operation. First, we see a critical loss of sensitivity. The film on the electrode acts like an insulating layer. The electrode loses its ability to respond to concentration changes, which is evident by the decreasing calibration strength. Second, we have reference electrode drift. The film clogs the porous junction of the reference electrode and changes its potential. Since every measurement is a comparison to the reference electrode, every successive measurement is inaccurate. Third, and this is the crucial point for the operator, it creates a false sense of security. An operator who calibrates infrequently would not notice this rapid daily deterioration. The instrument appears to be working, but provides unreliable values. The greatest danger is the masking of malfunctions. The primary purpose of a sodium analyzer, for example, is the early detection of a condenser leak. A contaminated, blinded analyzer will not report such a critical event, or will only report it much too late. We also wondered whether these effects could be transferred to other measurement parameters. The results confirm that this is a systematic problem of electrode contamination. We observed a similar effect in conductivity measurements. Over the test period, we observed a noticeable decrease in the measured conductivity. This is because the insulating FFA film also coats the conductivity electrodes and impedes the flow of ions, which the device incorrectly interprets as lower conductivity. Interestingly, some of our pH measurements showed no significant effects of contamination. However, we attribute this to the special chemical resistance of the reflex pH sensor we used, as other pH sensors were generally not immune and displayed similar results as the sodium. We saw a mixed picture with dissolved oxygen. Waltron's modern luminescent sensor showed zero degradation. An older galvanic oxygen sensor, however, showed a significant decrease in sensitivity, consistent with the observations of electrochemical fouling in the sodium tests. This underscores that electrochemical sensors in particular are vulnerable to FFAP fouling. What do all these results mean for practice? The use of FFAs requires a rethink in water chemistry monitoring. At Waltron, we have initiated a series of follow-up experiments to identify effective countermeasures. The results are preliminary but promising. Automatic cleaning cycles, as described in a 2012 PPCM article by Swan Analytical, appear to be an effective approach to keeping electrodes clean. Filtration is another option. Simple polypropylene filters showed excellent performance removing FFAs. It's unclear exactly how long they will continue to provide protection, as we ran out of time before reaching breakthrough at our concentrations. Filtration with glass wool was effective for preventing adsorption onto contacting conductivity electrodes, but unfortunately introduced sodium into the sample. UV treatment can destroy FFAs, but also affects conductivity and appears to lower the measured sodium concentration, possibly through chemical sequestration. It merits further testing. Technological upgrades such as double-junction reference electrodes or solid-state ion-selective electrodes could also significantly improve the stability of sodium measuring devices. We will discuss the results of these tests in future presentations. Until then, our clear recommendation is operators must be vigilant for electrochemical contamination from FFAPs, follow recognized IAPWS guidelines, and significantly shorten their maintenance and calibration cycles to prevent an unnoticed disaster. This concludes my presentation. Thank you very much for your attention. At Waltron, we believe that greater awareness of film-forming products can ensure safe and efficient plant operation. I'm happy to answer your questions, perhaps with a little help from my chemist friends, if they go beyond my technical expertise.